morning to all the participants and all the members present here for the session today on 3D printing and additive manufacturing. Before we begin with the session, I heartily and warmly welcome you all to have knowledge on the topic and practically be able to implement in your future experiences also. And I would also like to thank and acknowledge that under the guidance of our Honorable Principal Secretary Ma'am Anju Sharma and our Director Sir Nagarajan, we have begun with this 50 webinar series. It is an initiative taken by Knowledge Consortium of Gujarat. And before we further begin, I would like to introduce and mark the presence of Professor A.U. Patel, who is imparting his services as an advisor at KCG. I would like to equally mark the presence of Dr. Kaushal Desai, Associate Professor at the Department of Mechanical Engineering, Indian Institute of Technology, Jodhpur. Now I would like to request Professor A.U. Patel, sir, to give a short welcome address to all our participants and speaker also.
Hello, good morning to everybody. It gives me immense pleasure to welcome you all on behalf of KCG Knowledge Consortium of Gujarat. In today's webinar on unusual applications of 3D printing or additive manufacturing, I would like to thank our eminent speaker for agreeing to be a part of this webinar and share his knowledge with our professors and researchers. Dr. Kaushal Desai, Associate Professor, Department of Mechanical Engineering, Indian Institute of Technology, Jodhpur. Also special thanks to our respectable dignitary, Sri Nagarajan Sahib, Director, Higher Education, Government of Gujarat and CEO, KCG. Keeping in view of rapidly changing technologies, a series of webinars on emerging technologies, particularly for difficult subjects, have been planned to organize by KCG to give a boost to our education system by providing in high-depth knowledge on emerging technologies. I welcome and express thanks to all faculty members, researchers, scholars, students, and active participation and remain present here in this webinar. 3D printing or additive manufacturing is constructed of a three-dimensional object from CAD model of digital 3D model. The term 3D printing can refer to a variety of processes in which material is deposited, joined or solidified under computer control to create a three-dimensional object with material being added. For together, such as plastics, liquids or powder grains being fused together, typically layer by layer. One of the key advantages of 3D printing is the ability to produce very complex shapes or geometrices that would be otherwise impossible to construct by hand, including hollow parts or parts with internal truss structures to reduce weight. Fused deposition modeling FDM, which uses continuous filament of a thermoplastic material, is the common 3D printing process in use of 2020. Additive manufacturing of food is being developed by squeezing out food layer by layer into three-dimensional objects. A large variety of foods are appropriate candidates such as chocolate and candy, and flat foods such as crackers, pasta, and pizza. NASA is looking into the technology in order to create 3D printed food to limit food waste and to make food that is designed to fit an astronaut's dietary needs. In 2018, Italian bioengineer Sionti developed a technology allowing to generate fibrous plant-based meat analogous using a custom 3D bioprinter, mimicking meat texture and nutritional values. Thus, this 3D printing and additive manufacturing, a wide application, a visualization tool in design, a means to create highly customized products for consumers and professionals, as industrial tooling to produce small lots of production parts, one day production, human organs, etc. Our guest speaker is expert and he is also in IIT Jodhpur. So he will guide and explain everything in detail, and perhaps you will be able to understand entire topic after this webinar very well. So again, I congratulate and welcome our guest speaker, Mr. Desai. 01. Thank you very much. Welcome you all.
Thank you, sir. Thank you so much for your kind words, introduction, and welcoming our participants. And before we begin, I would like to have your permission that shall we wait for Nagarajan Sahab to join us, or shall we proceed ahead?
No, he is busy with election duty in West Bengal.
Okay, sir.
So may not be able to join.
Okay, sir.
But before you start, I request please give biodata of Dr. Kaushal Desai.
Okay, sir, sure.
So our listeners may have better idea about our
Sure, sir. Sure, sir. I take this privilege to introduce Mr. Kaushal Desai. Kaushal A. Desai is production engineer graduate from Birla Vishwakarma Mahavidyalaya and PhD in mechanical engineering from Indian Institute of Technology, Delhi. He worked as a guest researcher at Manufacturing Metrology Division, National Institute of Standards of Technology, Gatesburg, USA. At present, he is an associate professor at the Department of Mechanical Engineering at IIT Jodhpur. He has been instrumental in developing advanced manufacturing and metrology laboratories at IIT Jodhpur. His research interests are in the area of CNC machine tools, CAD, CAM, smart manufacturing, and new product development. Hopefully, I have covered all the aspects, sir. If I have left out, I would request you to please fulfill that. Thank you so much, and once again, I welcome you.
So with the permission of chair, I would like to begin my session. First of all, I am from Gujarat, and coming to Gujarat always in any form. In fact, as a student, I was a part of Gujarat. My basic schooling education was in government schools across Gujarat. I did my engineering degree from Gujarat, one of the top engineering colleges in Gujarat, Birla Vishwakarma Mahavidyalaya, in manufacturing or production engineering. And later it gave me an opportunity to rise to a level of a student in an IIT, which is dream for everyone across the country who is aspiring to be an engineer. And subsequently IIT, which is also set up by Government of India as a national education and institute of national importance, it provided me platform to build my professional career, starting from doing a state-of-art research at the IIT Delhi. Then it supported me to go to United States for doing my postdoctoral work, and then subsequently I returned to IIT Jodhpur as a faculty member way back in 2014. So when I joined IIT Jodhpur, it was a new IIT, and with the government funding and support of government, we could build state-of-art facilities in the area of advanced manufacturing, where this 3D printing or additive manufacturing process lies. So first of all, thank you, Knowledge Consortium of Gujarat, the Department of Education and Government of Gujarat for inviting me to share my experiences as an engineer in talking about whatever we do in terms of 3D printing at IIT Jodhpur and sharing it with the colleges and fraternity of Gujarat State on this online webinar on emerging technologies. In fact, when I got a call from Professor Patel, I was pretty happy and delighted to speak about this, because anyway, associating with Department of Education of our government of Gujarat is a pleasure, because it is giving back to my home state, something that I have gained in my life as a researcher. Although I'm pretty young, but almost a long experience in working in this this domain will help you to know a lot of things which are happening around us, which can be done better by 3D printing in the session. So to begin with, I would say that when I was given an opportunity to speak about this thing, honestly speaking, I was not aware of the audience, and it motivated me to build a presentation which shall motivate a young budding engineer to take up careers in this domain. Not only taking young career engineers to take up careers in this domain, but someone who is doing research in this domain in the state of Gujarat or anywhere. It would give him enough opportunities and thoughts to pursue research in different domains associated with 3D printing. And somebody who is an industrial professional working in the domain of 3D printing, maybe building machine to using it for different applications. It will also help those set of engineers or industry professionals to think about new applications so that they can expand their businesses. So with this brief understanding, with this brief introduction, I would like to begin my talk. I would try to be as brief as possible, because I know in online forums, speaking for 2 hours to a dead screen is a very boring experience for the speaker. And equally, it is an equally boring experience for the listener, because you are feeling that you are speaking to someone, but you are actually watching the video. So I would try to present certain thoughts. In between, I might take pause to hear back the questions which you might have posted in the Q&A session of the Microsoft team. And then we should have the exchange of ideas and thoughts at different points of time, and then we shall try to see that this 2-hour session is exciting and important for you in terms of getting the knowledge. So if you talk about 3D printing today, why is it important today? See, when I was a student way back in 1997, when I started my journey at BVM Engineering College and graduated in the year 2001, honestly speaking, I have not heard of this term at that point of time. Although the technology was taught in those times, majority of state engineering colleges, barring few IITs and NITs, were actually knowing about this. But then eventually when I went into an IIT, I heard about this and it excited me a lot. In fact, I did some courses in my studies at IIT to learn more about these processes. And if I see what I studied way back in 2000 and if I see today, I feel that it has become a significant, important manufacturing process today. It was not this important when we were students, but it is a very, very important process today. And I must accolade the efforts of Knowledge Consortium of Gujarat in taking up an initiative in inviting experts to speak about such topics, so that in spite of having non-availability of resources at various state level colleges which are in remote places, they would know about what the technology is. And this is what is an advantage of an online platform, wherein an expert is not required to visit Ahmedabad to interact with you all. Rather, I can sit in Jodhpur and speak about whatever I know over this platform. So please understand that 3D printing is an important manufacturing process today. So when we talk about manufacturing processes, different processes will come across your mind, starting from a simple process which you see alongside road, wherein a blacksmith is forging the tools which are required for different agricultural applications or different household applications, to a very complex process like you are using a CNC machine to build certain multi-axis components which are required for different space applications or aerospace applications or automotive applications. So this all belongs to a manufacturing family, and 3D printing is a relatively newer addition to that family. Okay, and what has happened is in last decade, because of the technological advancements, because of the capabilities of a process, because of inherent, the strengths and advantages of a process, it has become very, very important, equally important process as any other manufacturing process that we talk about today. So say for an example, if you look at the market survey, which was conducted way back in 2007, it says that the market for 3D printing process exceeded from 1 billion to 6 billion between 2009 to 2016. So if you talk about, it's a 6 times rise. So it's not a small number. So if you are having 100 rupee sales today, in 2009 it became 600 rupees sale way back in just 15 years of time. So it's a huge market which has grown. And in fact, if you look at the Rollers report, what they forecasted in 2016 is it's going to grow at an average CAGR, that is average annual compound return of about 31%. And if you keep growing at this rate, you become a huge business. So, and if you look at the forecasts which were made in 2016, which are valid till 2015, people are saying it's even going to grow at a much faster rate than which Wohlers reported. In fact, if you want to know that those who are budding engineers and those who want to know what are the newer technology trends, I advise them to see a journal which is published, or the articles which are published in a document called as Gartner. And Gartner's hype curve in 2018 presented different 3D printing technologies at different levels of maturity in the life cycle. So in fact, if you look at the most right hand side of your screen, this has reached to a kind of a mature level. And if you look at the left hand side of the curve, it is something which is actually being conceived in the mind of people. And in between that, between this left and right extreme, what happens is that technology grows, eventually expectations fade, and then it becomes mature. So say for an example, the concept of 3D printing, if you talk about today, has reached to a maturity level. So people understand that this is something which I can do via 3D printing, and it is a process which has a potential. And in fact, one of the commercial process like material extrusion has also become, which Professor Patel was mentioning in his talk, it has reached to a maturity level. In fact, plateau of productivity, when the technology reaches at the plateau of productivity, it is understood that the technology has started becoming mature now. A definition of maturity is a common person knows this technology and accepts this as a standard solution. In fact, the next zone, if you look at on the second zone on the right hand side, it is actually talking about slope of entitlement. So what will happen? I will tell you in a brief about any new technology. So whenever we talk about new technology, the first thing which will happen, which is seen on the left hand side, is an innovation trigger. So what will happen? People will think, can I apply this to a given problem? So that question which is coming into the mind of a people, this triggers about a new idea, a new innovation. So say for an example, if you talk about a 3D printing of consumable personal products. So this is something which people are thinking that whatever, I mean, Professor Patel was talking about 3D printing of foods. So can I say I think about eating a pizza, okay? And I don't want to go to Domino's or a KFC or a Pizza Hut or any food chain. And I have a machine in my home which can print, which can produce a pizza for me readily. I just think about it and it will customize the thing according to my needs. So this is what is an innovation trigger. I want to basically develop a machine which can print a pizza for me by the time this session is over, right? So this will give you an innovation trigger. Lot of people, lot of ideas in 3D printing which are lying on the left hand side of your screen are in innovation stage. People are thinking that, can I actually build a nano size component using 3D printing? So it's in the innovation stage. People are thinking that, can I use 3D printing in oil and gas sector? These are all in innovation stage. I mean, what I would say is people have thought about it and they are exploring. In fact, if you see one of the very important name which is lying here, it is called as a 4D printing. So people from 3D are now actually going to talking about the fourth dimension. So when we talk about 3D, these 3D are the three basic dimensions. On the other hand, when we talk about 4D, you are adding a fourth dimension, and then this fourth dimension is a time. So I am actually imagining the product which will change its dimensions over a period of time. Just say for an example, look at humans, look at our bones, look at our skin, look at our tissues. All this changes over a period of time. They either change the dimensions, they either change the properties, they either change the texture. So can I build a physical component, say can I build a water bottle which changes its shape over a period of time? Can I build a telephone or can I build a device which is originally printed, but when I put it into a practice, it basically changes the dimensions, it changes the property as a function of time. So lot of applications people are talking about, and these are in the innovation stage. So when you have an idea of innovation, what it will create, it will create a hype. So the moment I shared a few ideas, it triggered an adrenaline on your body, and then you started thinking about, hey, I can create all this via this. So you start working on that, put your all efforts, and then you reach at a peak of inflated expectations. So what do you think is this all hype that you create will take you to a level which is, I mean, you think you can win the war with this. But eventually when you reach there, you see around surrounding you, you feel that, okay, all this I cannot do, so I start dropping down a few things, and then you basically go to a trough of disillusionment. So that is a third stage. So what will happen is you will go to a trough of disillusionment, and then you will realize, okay, I cannot do all this, but I can do only a few things. I might think about that expectation, but then this is what is the reality. So it's a reality check. And when you fall, you actually start focusing onto a more realistic domain, and that is what is called as a slope of enlightenment. So any new technology, I mean, I was speaking to Professor Patel when at the time of invitation that all the technology trends which are identified by Knowledge Consortium of Gujarat are like this. They are at some stage in your Gartner's hype cycle. So 3D printing in its nutshell form has become a reality today. Certain technologies are into a plateau of productivity. Certain things are lying in form of innovation trigger. They say I can apply there. Say for an example, can I 3D print a drug? A lot of people are trying to print a drug according to a custom need. So it is somewhere in the, it was a reality a few years ago, but now it is going to reach to a peak of expectation wherein people would say, okay, these drugs I can build, these drugs I cannot build. And then you will go to a trough of disillusionment where you realize you remove all unnecessary options. So eventually, if you look at a triangle which is sitting here, for a few years it will have a height. And then eventually it would fall, and then you rise from there stating, these all I can do. So all these technologies, if you look at, these are the different technologies which are there in 3D printing or additive manufacturing, and they are at a different stages of their hype. Some of them are at an innovation stage. Some of them are in the inflated expectation stage. Some of them people have realized I cannot do this. Some of them people have realized, okay, I can do all this, and this is what I should be actually. So if you talk about dental devices, people have known this is what I can do in dentistry, and this is what I cannot do in dentistry, and let me grow on that business. So if you talk about human tissues, people thought this is what all I can do, but now people are realizing this is what I cannot do, so I might have to trim down my expectations. So all these 3D printing technologies are into different stages of their hype. Okay. And eventually in years to come, this is going to be, some of them will be a really commercial solution when it reaches to a plateau of productivity. That is where it will be available commonly in a market. So with this background introduction, what I presume for this talk is the audience is not knowing 3D printing at all. So maybe a few initial minutes I would spend on talking about the basics of 3D printing. And eventually we will go to some of the unusual applications which are there for the people who actually know 3D printing a bit. Where can they take their technologies forward, and some of the unusual applications. What do I mean by unusual? This is what we shall also talk subsequently when we actually go into that particular aspect. Okay. So if you ask to a layman or somebody who has a little bit knowledge of 3D printing this question, it says that what is 3D printing or additive manufacturing? This is what is a common question that you should have, and somebody who is a completely non-knowledgeable person, he would say, what bluff this person is making? Let me ask him this question, that what is 3D printing or additive manufacturing? So I would say that if you look at history, it originated as rapid prototyping solution. So another common name which you will find for it in the literature is rapid prototype. Now, what do we mean by prototyping? All of us have studied different prototypes, being it an engineer or a non-engineer, at one or the other point of time in our life. We all have studied prototypes. So these prototypes are the replica of the actual component. Say for an example, when my son was going to, he's in second standard, so when he was going to a school, he asked me that, what is this globe? So there is a very nice globe which we all see in early schools, which talks about orientation of continents and water bodies. It is not a globe, but it is a prototype or a replica of a globe. It helps me in realizing that the globe on which I am living is having a certain shape. This is what is my neighboring country without actually going there. Even if you go to a higher level schools, people talk about prototype of a galaxy. So we say that this is a sun at the center, and then sun also revolves and rotates about certain axis. There is an earth which is lying here. So these are all prototypes. See, when you go to a manufacturing industry, or say for an example, let's talk about any typical manufacturing industry. When they start having an idea of a design, whether that design will work or not in a market, or whether that design will serve its purpose or not, in order to check and evaluate that, what majority of manufacturing companies do is they prepare a small prototype of that. Okay? And a small prototype of that is actually tested for certain conditions. Say for an example, if you talk about automotives around you today, everybody talks about crash safety. Okay. So what people do is they don't make your car crash, but they actually prepare a prototype, and then this prototype is tested for real life conditions. And when you test it for real life conditions, you realize whether the design that you have thought is getting conceived, is serving its purpose or not. Now, nobody in industry, if you talk, is willing to spend money for prototyping. The reason being, it's a non-productive activity. Because you build a prototype, you don't earn anything on that. You test it, you realize you failed. So there is always a fear of failure. On top of it, it consumes a lot of time. So when you go to an industry talks about deadlines. So they say in 6 months you have to come up, and then if you say 3 months are gone in prototyping, they will say, okay, you are reducing my time to make it. So nobody would be willing to actually spend time on prototyping. On top of it, it is also involving money, because you have to build a prototype, you have to hire people who will actually build a prototype, do testing, produce results for you, and then you will start earning. So this prototyping was always a hurdle for majority of industries, because it's a non-productive but still necessary activity. So a lot of people were finding shortcuts on that, and the world thought at one point of time that, can I do this prototyping rapidly? And what do I mean rapidly is, I would like to create a system or a part representation rapidly before final release and commercialization for the purpose of different things. For the purpose of different functions. Say you have some design in your mind and you want to show it to your boss. So rather than building, can I build it quickly in a day? Or it can be as a complex product like a car, as I mentioned. I will build a foolproof car using prototyping tool, and then I test it, and then I'm more confident about my release. So it originated as actually a prototyping technique. Nobody thought, when it was invented in 1980, late 1980s, early 1990s, people did not think that this is going to be a manufacturing process. Please understand. It was just created as a system for part representation. They say that the actual part, I'm interested in representing it somehow rapidly. So when I build a prototype, so just say for an example, if you have some idea in mind, rather than describing that idea with word, you would build a physical presentation of that. It would always be more appealing to the people to whom you present it. They would be more convinced on the fact that this is what can be a reality. But this has to happen rapidly. Old days, people were doing that. If you ask me what were the questions, so you were making clay models, you were making wood models, you were actually making cardboard models, or you were making different things. Even if we go to engineering colleges today, in the prototyping stage, people always build this kind of prototypes, which are either made of cardboard, wood, plastic, paper, whatnot. A simple prototype can be a sketch even. But this all has to happen rapidly. The question is, why is it done rapidly in this process? Because the process is rapid, not just time it takes to build the part, but because this is realized through the use of computers throughout the process. So please understand that when the process was innovated way back in 1980s, 1990s, the computers were also realized by then. So amongst the entire manufacturing value chain or a process chain, this is the first process which was thought after invention of a computer. So what happened is, say if you talk about that blacksmithy, this process was not thought when the computers were there. It was thought well before computers were thought. Today, you might have a computer-controlled press, but the basic process was thought well before computers came into the world. So the philosophy of a process was never designed. The philosophy of a process was never designed with computers. It was philosophically thought as a human-driven, manual, or a power-driven process. It was never thought as a process that would run with computer. So I was not having a computer when I thought about hitting a hammer on a heated part. The computer was not in my mind when the process was thought. But the advantage that people had when they thought about 3D printing or additive manufacturing is, I had computers, and they said that everything in my process, I want to realize via computer, which implies that the human involvement in the running of a machine would be almost nil, zero, or negligible. So it is completely realized through the computers. So there is no human involvement, which makes it rapid. Now the question, as I introduce computer, then the question that you will ask me is, how computer will help? Why a human who was making cannot make it rapidly, and how computers can help? Ideal thing is, let us say we think about innovation. I have built a model on a computer because you know all CAD tools. So by the time in 1980s, whatever idea people had about the physical product, they were actually building it on a computer. And you think that once it is ready on a computer, which is a virtual model, can I just press a button, say make it, and then in some time it would be ready. It is just coming out to me in form of a home delivery in some or the other form without any human interaction. So the ideal solution which was innovation trigger was, I have a computer representation available in 1980s, 1990s. Can I build it by just pressing a button? I don't want to talk to anyone. I just press a button and then I have a component ready. This is what was an innovation trigger, which created a very high expectation. Then you have gone down and then you have reached to a reality where this is what I can do and this is what I cannot do. So this is what people thought. Now, how things will happen rapidly? Because imagine a scenario wherein you have some idea and you have to get the things made, you have to talk to a lot of people. Although you have a machine, you need an operator to run the machine. You need certain tools and all that to operate that machine. You need power and energy and whatnot, and you have to manage all these things. Here the thing is, my computer is connected to a machine. I press a button, the things will go to a machine and the machine will start doing things on its own. At the end, when it completes, I get a message on computer says, ready for delivery. I go to a machine and I collect it. So this is what was the philosophy. And this is how people started building a 3D printing. So the overall philosophy was, as Professor Patel also mentioned, that computer model or a physical representation of a virtual representation of a physical object on a computer was called as a CAD model. And you transform CAD model directly into a finished product. And this is what will give you, so what advantage do you see or what advantage do you expect if it is reality? You will be gung-ho, right? You don't need to worry about manpower. Labor was a big problem in COVID times. A lot of manufacturing engineers would tell me, if this is what can happen, I would jump to buy this machine, right? So there are many advantages. You are not relying on an operator. You are not relying skill of a person at all. You are not relying on a lot of other aspects that this person will give me that person will give me this. If they all come together, I will build this. All these questions would disappear from the mind and you will become fearless in designing. You will become fearless in manufacturing. So there are many advantages. So before we actually look into 3D printing, let us look at a couple of approaches. Okay. So a couple of approaches that how the component is made. If you look at historically, say this is a component that I want to make. This is just, you can say a cross section. And then it is having some depth. So some thickness it has, which is not shown because we are seeing on a 2D plane. So if I want to make this, and if you go to different people, one person would say, okay, I would cut this, I would take a larger size component and I would cut a shape out of it. So this trimming of the unnecessary area from the raw material is referred to as machining. Okay. Another set of people would say, why are you cutting? You are producing a waste. Rather than that, you break this into two pieces and then you stitch them. And there is a commercial variant available. A lot of people would say this is welding, joining, brazing, riveting, whatnot. So there are manufacturing processes which are available to achieve this. So this can be another approach to realize this. A third set of people would say, no, what I have is I have a die and a punch, and I would compress the component which is near net shape between these two in order to get the required shape. And the operation which we all call as, those who are manufacturing or mechanical engineers, they know this, they call this as a forging. But what do they do in 3D printing? is philosophy. And if you look at these three, to reach to a final object, these all three follows different routes. Say if you talk about machining, you are going to cut. That means you need a mechanism to cut. If you are talking about joining, you are going to need a physical mechanism to create a joint. If you are talking about forging, what you need is you need a punch and a die, which is tooling, and then you need a component which is having a close shape to what you are seeing. Although one more option I have not included here, there are many more options, but these three, if you look at, the three have unique approaches. When you talk about rapid prototyping or additive manufacturing, it has also a philosophically different route. What it says is, you basically slice a component. So what you do is, rather than you have a final idea of a final shape, what you do is you create slices. You know this, and you know the sequence in which these slices are to be joined. So you join all the, and you design a joining mechanism for these slices, and then you build an object. So what you do is, these are all different slices, they are joined together in order to realize a component. And this is what is the driving philosophy for building a component using rapid prototyping, 3D printing, or additive manufacturing. Please understand that. Okay. If you look at the example, I would say that you want to design a very elegant and aesthetically looking teacup, because now almost we started speaking and it's almost 30 minutes or 20 minutes now. So you are tired and you want to have a tea and you are designing an elegant teacup. So there is a computer model of a teacup that you created. And what you want to achieve is, you want to actually achieve a 3D printed cup of that. So you can actually build it. So what you have done is, you can see this is a reality today. All these layers are built, deposited together, and a cup is generated. In fact, the idea is not new. Our idea was not new in 1980s and 90. This was already existing in practice. So if you look at, this is the physical object which you are seeing on your right hand side. This is a structure in Europe. You can see a very complicated structure is made up of slices. Okay. And somehow they created a mechanism to join these slices so that this was built. Although it is all hollow, this is a finished structure. There is a cylindrical connection at the center. But what I did here is, to get this a very complex curve. What I did is, I prepared a CAD model. I need a mechanism to cut it down the slices. So all this slice information I have, and I will communicate this slice information to the machine, and the machine would generate an object. So this was an overall philosophy. So the overall philosophy of a process is what? You build a CAD model as an idea. In your computer, you have a mechanism to slice the object. Okay. So you create a slice. There is altogether, this second operation also happens on a computer. So first and second operation is done on a computer, and this computer will send an instruction to the machine to actually generate a physical object. So in the third step, your physical reality happens. Step 1 and 2 merely happens on a computer. It also helps you in saving the time. The reason is, your machine will not be occupied. When you are doing this, it can do some other activity. So there is inherent advantage of a process, because the machine runs on a completely unattended mode. Because the instructions will go to run a machine from the computer. You do not need an operator to run the machine. Say typically like a forging machine, or a machining, or a lathe, or a milling machine, or a drilling machine. You don't need an operator. The machine will run on its own. You need to generate an instruction on a computer. So if you look at 3D printing community, lot of people work in these two rectangles. And these two rectangles are the software part of 3D printing. Meanwhile, there is a big challenge in terms of joining, because in Gujarati we all know there is a proverb which says Sandha Tetla Bandha. And here you are creating infinite joints, and the challenge is in terms of how that all layers which you created, they all will remain together so that this looks like a World Cup, and when you hold it in your hand, it simply does not bend because your joining was not proper, or it will break. So there are challenges in joining. So there are a set of people who work on what are the challenges. There are challenges in terms of creating this slice. It's not simple. When you give a command to computer, there is something at the back of your computer, some program which you have written which does this slicing, some mathematical equations that you have written in form of a software code which does this. So there is a challenge. So a lot of people work in this domain, a lot of people work in the physical area, and then that is where the primary breakup happens in the community. So a lot of people say that there are 3D printing software people and there are 3D printing hardware engineers. So hardware people look at more in terms of how to improve a process or how to design a process so that it looks like a single component and it acts like a single component when you put it into practice. And the software people make sure that this slicing and all happens systematically, beautifully, and I don't lose an accuracy of a component in the process. So this is although this appears very simple on a piece of paper, the technology is very, very challenging, and there is a dearth of research that is happening all around with a lot of articles, lot of journals dedicated to this area available today. Okay, so it's a big field. Now, those who are working in this developing a physical object, they basically worked on different technologies. So they say that the raw material that I pick up, because to build this physical object, I'm going to need some material. And you know the material will be available in either of the three forms, which could be a solid, or it could be a liquid, or it can be a gas. So there were people who chose solid as an option and started building this physical object, and they picked up a solid wire. They said that I will melt a solid wire and I will deposit it, and then eventually it will solidify in form of a layer. On top of it, again I will build another layer. This is one of the very common and a popular approach which uses a solid wire. And the process is known as fused deposition modeling. A lot of people said, I don't want to pick up wire, I can pick up powder also. So a lot of people actually picked up powder. So it's a solid material converted in form of a powder. And then somehow you deposit a layer of powder, and then you create a thickness layer from that powder, which is a solid entity. So when you do some action, it becomes solid. Eventually, you use that as one layer. On top of that, again, you deposit a powder, you do some action. So both these layers will get joined, and subsequently different processes were developed. There are two very popular commercial processes available into that route. One is known as a 3D printing. There are two more variants which we shall talk subsequently, and another variant is called as selective laser sintering. A lot of people said, I don't want to pick up wire, I don't want to pick up powder. They said, I will pick up a foil. So a lot of you people would be carrying a food in your tiffin, and then to keep it hot, we all use a foil, aluminum foil, right? So in aluminum foil, I wrap the food. The advantage of aluminum foil is, or a structure like aluminum foil is, it is already available in a layered form. See, the challenge in wire and powder is I am building what? A layer from something else. But here I have a layer readily available. So what I do philosophically in a foil is I put two foils together, and then eventually I remove unnecessary areas, because the foil would be available in a standard shape. So I will cut the foil to some shape which is available in that layer, and then I will deposit one layer, one foil over the other foil, And you all know there is a technology available to do that, which is called as a lamination technology. So you all get your mark sheets and everything, the papers which are to be preserved for a longer period, laminated. And that is why the name given to this process is called as laminated object manufacturing. There is another route, as I said, you can not use liquid, but there is an intermediate route wherein you bring a paste. So paste is something which is like a Colgate or a mushy state. So it's a semi-solid state. I can also use a semi-solid state to deposit a layer. Eventually, I have a mechanism to solidify the paste into solid shape in the layer, and then I deposit another paste layer, and over a period of time, I build a component. If you don't want to use, the other extreme between liquid and the other extreme of a paste is a liquid. So I can also use liquid, and there are different routes in the liquid route. So what you do is you increase the temperature of a liquid by heat. The process is called as a polymerization. I can apply light on a liquid, so it gets cured, it converts itself to solid. Or a third option is I can always incident a light of a certain frequency. So that is called as a stereolithography. In fact, a lot of people are exploring, can I convert gas to a solid directly? And those who are researchers in this domain, they would be knowing a technology called as LCVD. So this is where people are trying to build layer of a solid from the gaseous state itself. So ultimately, this is the state that I pick up from which I build a layer, and then I build subsequent layers, and these subsequent layers together will result into a three-dimensional component. So these are different 3D printing technologies, and a lot of people build. And then many technologies, when people start building, some standardization is necessary. So there is a body called as ASTM, and this ASTM has given classification of 3D printing or additive manufacturing into not seven, but actually 8 groups. So they say that one of the governing principles that you use for building a component can be extrusion of a material. So if you remember, we talked in a previous slide about a wire. So what I do is I have a heater. In that heater, the wire goes and the wire melts, and what comes out is a paste-like material, which is an extrusion of the liquid material. And the process which was lying into that family were known as fused deposition modeling. The technical name, acronym which is given to that is FDM. There were powder-based processes, as we discussed. So that technical name given to them was a powder-based fusion. And another name which was given was selective laser sintering, SLS. 2 more variants were also, clubbed together into a family, which are mainly depositing a liquid jet and then letting it solidify. So that was called as a material jetting. We shall be talking about all this subsequently. Another variant which was developed was a binder jetting. Another classification which they gave was a sheet lamination or a laminated object manufacturing. Converting liquid directly using a light source, those processes they put together into a VAT photopolymerization family. In fact, 7th one was developed very recently, maybe a decade ago. It is called as a direct energy deposition, wherein people are talking. It is not developed as actually a prototyping process. It is developed as a final component manufacturing process. We shall talk about it subsequently. It is a DMD. Anything which is not belonging into these 7 cases was being put as under a miscellaneous category. So this was the classification which I wanted to discuss about the additive manufacturing. So before we move further, what I would like to do is I would like to know, in case if the participants have any questions, please feel free to ask it at this point of time. We shall have a pause for a minute, and eventually, if you don't have any question, we shall go to the subsequent part of a discussion, which is going to discuss all these processes in 1 slide each, bringing commercial solutions related to that. So if you have any questions, please feel free to ask at this point of time. Okay, so let us start back. So in fact, if you look at, we talked about 7 variants of the processes. And one of the first and commercially very, very important variant of a 3D printing process is a fused deposition modeling. So what do you do in this fused deposition modeling is you take up two wires. These wires are made up of two different materials essentially. These wires would go into a heater chamber. You can see a magnified diagram of a heater chamber on your right hand side. So what happens is this heater chamber would heat the wire and it would generate a liquid or a pasty material out of it. Okay. What is the role of these two wires? Say for an example, I am building a component which is like a dark blue color. Okay. So when I will reach somewhere at the middle, say somewhere like an eye section, when you reach somewhere here at, what will happen? I will deposit a thin layer. And if I have a structure like this, if this blue colored entity is not there, then what will happen? The material would fall down. So what I need to do is I need to create a support so that the material does not fall down. So this material is called as a support structure material. So if you look at the wires that you use, you typically have two wires. One is a build material wire. Build material wire is a material for which you want to build a component, using which you want to build a component. And a support wire is a wire which is used to create a support structure. And this support structure would be doing the task of supporting. The other important requirement that you need to build in a process is because when I build, this would be built as a cuboid then. Okay. Now what do I need to do is at the end of a process when the component is ready, I have to remove this support material. So this support material removal, so when people have to think, a lot of people work on designing what combination of a build and support material I have to use. The classical support material which I would like to build would be water soluble. So I put this part into water. The build material does not melt or does not get soluble into a water, but the support material will become soluble in a water like sugar or salt, and then it would dissolve. Eventually, I would be only left with a physical component. So this process uses two wires, as I said, a build material and a support material. Essentially, the input is in the wire form. And so you basically put a deposition of a material, the layers fuse into one another. And that is why the name of a process which was given as a fused deposition model. In fact, if you look at commercial installations today, a large number of economic installations across India, across world are these FDMs. In fact, there are many companies, even at a local level, within India, not within India, within Gujarat, not within Gujarat, at Ahmedabad itself, there are people who make this kind of machines. And in fact, these machines come in different variants today. I am talking about one of the biggest 3D printing or a FDM machine maker in the world, Stratasys, which is a US-based company. It makes all three variants. They make a machine as small as mounted on a table, which are called as a tabletop systems for making small products. They also make general purpose system. In fact, this is a diagram this is a picture of a machine that we have at IIT Jodhpur. So this is a general purpose system. This is not tabletop, but this is a little larger. And then this can build relatively a moderate size of component. A more commercial variant, which you will see in industry, are much more precise. And these are called precision machines. So FDM as a process, if you look today, has become very, very common. The essential philosophy in FDM is what? You use wire. The wire is melted into a heater. The liquid melt comes out of it. And this melt is deposited in form of a layer. And then one layer fuses over the other layer, which eventually results into a functional component, which is aimed by a designer. So this machine is connected with the computer. And the computer will generate what geometry it has to deposit in each layer. So that slice information which we talked is communicated from a computer, and then this machine converts it to a reality. A second variant, I mean, in fact, not a second variant, but in fact, if you look, just put this keyword in Amazon, there are 3D printing pens which are available costing few thousand rupees. So this is a 3D printing pen. There is a wire, there is a heater, there is an extruder, and then you can see you can build an Eiffel Tower. This is available now into schools. Lot of schools and all to give an idea about how this process works. And in fact, this is, I would say that this is available as a toy replacement. In fact, I have this in my home for my kid, and then he knows how to build a component using this. You can build a 3D component, just like it is a good replacement of building blocks. Only thing is, you have to throw it. You cannot reuse and you cannot make another component out of it. You have to build another component separately, and then the wire is available in form of a cartridge. In fact, there are multi-axis printers people have also built. They have mounted a torch on a robo, and then the robo will give you a freedom of depositing it at any angle and many other advantages people got. So FDM today is a commercial variant, and lots of industrial companies today use FDM exclusively for different applications. Another process variant which we talked about, which is called as a selective laser sintering or a powder bed fusion, it uses powder as a raw material. And if you look at the left hand side and right hand side, there are three chambers. The first chamber, which is on the left hand side, is containing powder. The one on the right hand side is also collecting the powder. The central chamber is a build chamber. So what happens is, two chambers supply the powder, and then the central chamber is actually place where the building happens. But as the thing is in a powder form, what you need is you need a heat source. So this heat is applied to the powder to melt the powder, and the powder particle will get connected or adjoined with each other, and that is what is referred to as sintering mechanism. So you are sintering the powder particle by application of a laser. This is called as a laser sintering. And you are not doing it everywhere. You are only doing it at area where you want to create a layer. Because my entire build chamber, if I deposit, I will get a cuboid. Remaining portion, certain portion I want to selectively sinter, other portion I don't want to sinter. That is why the process is known as a selective laser sintering process. So only selective areas you expose the laser, it will get melted. The remaining areas would remain in a powder form. And then this thing progressively moves downward, slowly it builds a component. The other two chambers will move upward while supplying the powder. So what will happen? I'll coat one powder layer. I'll selectively sinter it. The chamber would move down. The other two chambers would move up. The powder layer would be spread. Again, I'll do sintering. So the combination of up and down motion between a build chamber and a powder chamber, accompanied with controlled heating of a laser, would give you a 3D component out. The typical advantages of this is, because the powder is available to act as a support material, it is very different compared to an FDM where you don't need a support material. So if you talk about an FDM, you all need a support material, but when you talk about an SLS, at the bottom you have a powder, as you can see here. Even these hollow portions have the powder. So you don't need to create a support material to ensure that the material does not fall, which you have deposited in a semi-solid state, because there is a powder to deposit. So this is an advantage. In fact, the other primary advantage is I can build a very large number of components. See, what I do is I have a big chamber, 10 different components are coming to me for the purpose of building. I can put all of them at different locations. All these components, if they are made up of the same material, can be built into a same setting. So this is a big advantage of a process. Well, at the end, what I do is I take everything out, I clean the chamber. It becomes an empty chamber with the table at the top, and the other two powder feeding chambers I'll keep feeding like powders. A third variant, which is of a great interest to the industries, is a material jetting. So what do you do here is, you know that there is a laser printing or an inkjet printing. So what do you do in an inkjet printing? If you are all aware about inkjet printing, then what do is you spread ink at selective locations where you want a letter to be highlighted. So there is an inkjet head. The inkjet head sprays the ink, and then you have typed certain things, so it will and if you really see this inkjet print using a magnifying glass, you will see that there are dots. So what this process variant does is it supplies liquid form, it supplies liquid particles, it spreads these liquid particles on a piece of paper or on a platform selectively. So what it does is, you can see that the component that you want to build is made up of some material, but it is also going to need a support because liquid cannot hang. So you have to create a support structure. So it will have a nozzle can supply multiple liquids actually. So what you do is that you can see that there are two material. One is this is a statistics diagram. So full cure S and full cure M are two different materials. One is a support material and one is a model material. So all nozzles which you have can supply both the things, and you can see this white portion was actually a support material and this black portion was the material of a component that you want to build. And then eventually the table would move down, and then you keep doing printing. It would build a component over a period of time. Another variant, which is made in a proprietary technology of a tech company by the name Exxon. What do you do here is you basically extend the SLS process, which is using powder. So you put a layer of a powder. You do not apply laser to sinter the powder. Rather, you use a binding material. Say something like a glue. So between two powdered particles, this glue will go and it will create a bond between these two powdered particles. And then eventually you can build a component. So this again does not require a support structure like the previous material because the things are available in a powder form. And when you open up a component, you can actually get a hollow shaped without removing the supports. You don't need to remove support because it's available in a powder form. In fact, all of you have seen lamination or a sheet lamination process. And I was talking about a foil-based manufacturing. So what do you do in a foil-based manufacturing is you have a table, you put a first foil, you cut the portion which is of not interest to you, leaving only the portion of interest available for you available. The table moves down, you bring another layer, you carry out a lamination, keep removing and lamination layered in a controlled manner. You generate an object via laminated object manufacturing. Please understand, laminated object manufacturing is a process where you are not going, the area that you will remove is something which is of your interest, because you are not going to remove the portion where the material has to stay. So typically, if you look at the sheet that you use, literally, when you expose heat, the liquid will become vapor. The foil will become vapor, and only the area of interest, the layer of interest would remain. Subsequently, a second layer would come. Eventually, it would deposit one over the other, and then you get a 3D object. In fact, this is a very exciting example which you might have gone through when you have gone to a dentist. So, if you go for a tooth filling, what do they do is, they put a liquid or a semi-solid entity into the canal, into the cavity that they created, and then they expose a UV light on it. So what will happen under the exposure of a UV light, that liquid or a semi-solid particle which has been filled into your cavity, they become solid. So this was philosophically extended in building a 3D component. So what you have is, you have a container which is filled with the liquid. Okay. Imagine that this Y platform is at the top when the operation commenced. This light you exposed on certain area of your interest, that area became solid. This Y platform will keep going down. You will keep exposing this UV light on selected areas, and then eventually you will build a 3D component out of it. So this is a stereolithography variant. These are also available commercially. In fact, the next family of a process which is called as a direct metal deposition, this process is thought as an additive manufacturing process, not as a prototyping. So if you talk about variants that we have discussed till now, they all were thought as a prototyping technique. But eventually people realized why I cannot build a functional part using this. So what happened is people said, I want to deposit metal now. But the problem and challenge with metal are very different compared to plastic and powder. So they eventually developed variants. Now, in fact, many variants are coming. Last 10 years, if you have seen large number of variants in this family are developed, 2 of them are very popular. Wherein what you have is you have a metal wire and then you have an electron beam. They both interact, it will convert it into a particle, and then that particle is deposited into a controlled way on to generate a layer. Eventually the build platform moves down, you deposit another area, and this process is called as a direct metal deposition. In fact, other variant which does not use a wire but it uses a powder. So what you have is instead of wire, you have a powder coming. It is something similar to a coating wherein you coat a layer, eventually you coat another layer. A series of layers together would help you in building a metallic component. So direct metal deposition was not thought as a manufacturing technique. So what I mean essentially by a manufacturing technique is you are aiming to build a functional component and not a prototype. If you talk about previous 6, the aim is to build a prototype because they were developed in a time where the process was explored as a prototyping technique. But if you talk DMD, DMD is thought at a time where people were actually talking about building a metallic component which is physical. It's not a prototype, it's an actual product. So DMD was majorly thought for metals, not for plastics and other family. It was thought as an additive manufacturing process. So this, if you look at this slide, if you look at this part of discussion, this 7 or 8 slides that I have talked about, this should give you a broader understanding and idea about different variants which are available in a market to build a component via 3D printing route. What do you need is you need a computer. When you buy a machine of any of these variants, they will give you a software. This software will help you in converting your CAD model to a layered information. So that software would be available to you. So you can build your CAD model using any of the software or your customer will give you. The software which is supplied with the machine will accept it. It will help you in converting it into layers. It will also help you in detecting the problems that might come during the printing, so you can fine tune those problems. Eventually, the software would help you in connecting with the machine. So when you are ready with the layered information on a software, the information is communicated to a machine and the machine will start building the component in a layered fashion. So this is what all will come as an integral form. So please understand, you can have a variant amongst any of these 7. The software part would change and it needs customization depending on the machine. Say for an example, in a laminated object manufacturing, your requirement would be very different. Say you have to cut the excessive material and then ensure that sufficient lamination pressure is applied. But say for an example, when you go to a selective laser sintering, in selective laser sintering, your requirement is not lamination. Your requirement is to generate a path for laser to hatch certain area. Or if you talk about fuse deposition modeling, the requirement is very different. And that is what you have to appreciate that every technology has their own advantages, limitations, and that needs to be supported through a software. So there is no universal software which will say, okay, I can supply the instruction to all the 8 variants. Maybe in years to come that might become a reality, but that does not exist commercially today, or it is not very, very popular commercially today. Now, so once you are familiar with these processes, there are, you know that there are, some typical applications, because the process was thought as a prototyping technique. And then it was extended to some of the applications. Say people said, if I can build a prototype, why can I not build a part directly? So what is wrong if I want to build a part directly? So people have already extended 3D printing to an additive manufacturing. So additive manufacturing is a direct digital fabrication. What people imply, 3D printing or rapid prototyping solutions are only aiming at developing prototypes. While an additive manufacturing process aims at developing a part directly out of a machine. A part means it can be readily used. So you are not limiting yourself to a prototype. So you are not restricting yourself to say it's just a demo. It's an actual component. So there is a difference between a demo piece and an actual component. So people have already extended this technology for direct digital fabrication of production parts. Your production part may be made up of plastic, may be made up of metal, may be made up of composites, may be made up of ceramics. So today there are commercial variants that can make plastic components directly using this route. Metal components directly using this route, composites directly using this route, ceramic components directly using this route. There are commercial solutions available in a market. You can buy, you can install, you can start a business. Another typical application where 3D printing has penetrated other than prototyping was an investment casting operation. And Gujarat is a hub for a lot of investment casting companies. In fact, I know a couple of people in Rajkot, something like Delta Technocast or something like Tamboli. They all use casting, investment casting as an operation. What was a bottleneck for them in old day? They have to develop a tooling for their process. So tooling does not produce a component directly, but this is something extra that you have to make so that your component can be made fast. So a lot of people try to make that tooling for a process like investment casting using 3D printing route, and today commercial solutions are available. So if you talk about wax patterns that are used in investment casting operation, all these wax patterns are made today using 3D printing. Majority of industries use that, and they have replaced the conventional way of making those wax patterns, which was something like an injection molding. People don't use injection molding route anymore. They use 3D printing route, but injection molding was making a tool which is a pattern for an investment casting. Pattern is a tooling. You need to have a pattern to make a component. That is what is a tooling. So this tooling can be made with 3D printing route. In fact, people have developed fixtures for machining. Many other things people have come up where it can be done. In fact, jewelry industry and some of the sculpting people have also adapted 3D printing as a standard process today. So these 3 applications, if you look at, they look an obvious extensions kind of thing. If I can make a prototype successfully, why can I not make a functional part? I can always make a functional part successfully. I can also make tooling. These were obvious applications. What we are going to touch upon in next 30 minutes is something which is unusual applications. So unusual applications are not accidental or obvious. These are some of the applications where people are looking 3D printing can be a game changer. Okay. So let's look at some of them in a list here, and then we shall discuss each one of them one by one in my subsequent discussion. 3D printing, when people innovated and thought about, nobody thought it as a process which can be extended to biological applications. What do I mean by biological applications is, can I build prosthesis, or can I build my organs which goes into the body as replacement, or can I build drugs using this route? Nobody would have dreamed about it. And that is why it is called as an unusual application. But when people who were working in medical field, they saw, oh, this is what is happening in a 3D printing. They thought, I can also do something meaningful for my sector. So today, this 3D printing has penetrated into a big way in medical industries, biological applications. Today, if you talk about the market of 3D printing, it is not into manufacturing, but a big market is there in medical and biological applications. In fact, if you go to majority of places today, the bioscience and bioengineering departments of those places are talking about 3D printing, bringing into their applications in a big way. Another sector, which is civil engineering, and today people are talking about buildings via 3D printing. Can I create an entire 3D printed building? Because if I can create that, a lot of things become very easy for me. So people are thinking about, if you talk about civil engineering applications today, a lot of people are talking about developing buildings via 3D printing. Building does not necessarily mean the houses. It includes houses, but it includes sculptures. It includes monuments. It includes many other applications within that building category. In fact, Jodhpur is one of the city which has a good gift of government. So we are an IIT here, which is a technology institute. We also have AIMS in a city. So All India Institute of Medical Sciences. So we collaborate with them on biological applications. Not only that, Jodhpur also has a central institute, a government institute, central government institute on footwear technology. So it is called as a Central Footwear Technology Institute. So a lot of people in the footwear technology and footwear industry are today talking about, can I use 3D printing to build footwears? Okay. In fact, the fourth institute in a Jodhpur city, which is again of a national importance and very important from the other aspects, is the fashion designing. So Jodhpur also has a National Institute of Fashion Design. So people are thinking that, can I use 3D printing in fashion design? Can I make clothes? In fact, Ahmedabad has NID, so National Institute of Design. And this NID, if you go, NID talks about using 3D printing into fashion designing in a big way. Why I am calling these unusual applications, you will appreciate the fact that these are not obvious extensions. If you look at top 3, they are obvious extensions, but these are not obvious extensions. But I would say that this is where there is a big application, and this is what is going to be the future. In fact, we all use wonderful furniture in our house for decoration of homes. And can I use 3D printing in home decoration and furnishing? Can I use 3D printing for building this? The advantage is, if you all appreciate the application, say if you look at biological application, let's talk that aspect a little later. In fact, Professor Patel also mentioned about NASA exploring making of food via 3D printers. So people are exploring 3D printing of food in a big way. It's going to be a big business now. And in fact, for a country like India, which is agri-driven economy, if I can make a solution which can, at a farm level, if a farmer can print a food just by installing a machine, it would be a big breakthrough for a country like India. In fact, developed countries have tire industries which do a lot of innovation in tire design and tire manufacturing. So the wheels or tires of automotive, see, we went from a tube tire to a tubeless tire. In fact, if you talk to people in Michelin or Bridgestone, they tell that the future tires are 3D printed tires. So we shall be talking about these all applications maybe for next 20 minutes of time, which shall allow us to cover the entire package into a 2-hour window. Now the question that should arise in your mind is why 3D printing has become a choice for this kind of unusual application. Please understand, 3D printing is a process that is supporting mass customization requirements. Old day, when people fought World War and the time after that, subsequently people were talking about mass manufacturing. They say when you make things in large quantity, it is economic. In fact, 3D printing can support the exactly contradicting requirement, which is a requirement of mass customization. So mass customization means what? Every individual has a different choice. And my manufacturing should not be governed by my own rule, rather by a customer rule. So in years to come, you will see, in fact, you are seeing that as even reality today, that number of varieties of a product are increasing. Why they are increasing? Because every customer has a different need. And my manufacturing should support that. And this 3D printing or additive manufacturing has innate strength to support this requirement. Why? Because if I can build a model, if I can slice a model, my machine should be able to build that component. And the amount of effort required in changing from one component to other component is minimum in this route compared to other process. Say for an example, if you talk about machining or forging, you need tooling. This tooling is changing when you change the component, and tooling is costly. You don't need tooling here, that difficult. So if you look at biological application, every human is having unique dimensions of their organs. Every human has a unique requirement of a drug. A drug that will work on you does not necessarily work on me. It might produce some side effect. So everybody's requirement is different. So I need a product that can be customized for a mass. Say for an example, if you talk about footwear, the footwear that I like, necessarily you may not like it. The sole that will work in a footwear for me will not work in a footwear for you, although our both leg sizes are same. Because of our different walking abilities, which are called as a human gait. The food that you like, I may not like. You may feel it spicy, I might feel it okay. The way in which your automotive car tire will wear out, my automotive car tire will not wear out in the same way. If I talk about fashion design or home decor or furnishing, the furniture that you like, I might not like. Please understand. So I cannot supply a standard thing anymore because people are asking for changes and people are ready to pay for that today because the purchase power of people has also gone. So these unusual applications are the future of 3D printing actually. Say if you talk about human body, today people are talking, if you talk 3D printing of implants are the parts, are artificial parts that will go into human body and serve the purpose. So 3D printing of implant is a big business today. If you talk about, you can build cranial prosthesis. So you can see a replacement of it as a prosthesis application, a surgical guide you can build a scapula prosthesis, you can build a knee prosthesis, you can build dental implants, you can build interbody fusion cage, you can build acetabular cup, you can build hip prosthesis. Please understand, I cannot build this in mass. Every human will have a different hip size. Therefore, the hip prosthesis that I build would be different. So what I can do is I can have a solution actually which can build a custom hip for the requirement of humans. And this is what root additive manufacturing or 3D printing will offer in implants, because implants are to be customized as per patient needs. So 3D printing of implant in years to come would be reality. You will have no problem in terms of fitting and all these implants into a body, because this is all tested from your human body. So you take an entire CT scan or X-ray, you look at a defect, you design by sitting on a computer, you reach at a product on a computer, then you tell your machine to build it. So it is designed for you. It is not designed for someone else. Please understand. The other medical application is typically in a lot of medical applications, people build silicon, and these silicon structures are usually soft. So this prosthesis which we talked, sometime they are to be built using a softer structure. Say something like, a lot of people, in fact, I was talking to one of the doctors in AIMS some time ago, and then he said that I have a very different requirement of building an ear. Because of some reason this person has lost an ear, the current way in which I can build a prosthesis for him looks like this. So what I do is I build, it's like your human teeth prosthesis. You remove your all teeth when you get old, and then you put a teeth prosthesis. Similarly, this ear has gone worn out. Now this is flexible, this is not rigid. So this is built via silicon. And the conventional way of building it currently, you can see, it looks as a separate part. And as a human, I don't like having such a thing. Although I will be fine with that, I am just using it for the purpose of looking as a complete human, but still I don't like it because it's not looking good. But in fact, there is a 3D printing route available in developed countries now. It is at a lab stage wherein I can build a wonderful silicon structure via 3D printing route, and it will fit exactly on me because I have done reverse engineering. I have designed an ear because I have one ear intact. I took a mirror image and then we build it. It's exactly looking like that, and I fit it. It doesn't look separate ear. In fact, people are exploring designing of a drug delivery systems today. So this is what is a catheter wire, and this needs to be sometimes creating problems. So people are today talking about, can I design this via 3D printing route? So this is a very unusual application what people are looking at. In fact, a lot of material that goes into our body should be biocompatible. Say something like a bone that I put in. I don't have a bone, and that bone we have to replace with a new bone. So this bone or the cartilage or a skin or a wound healing muscular grafts or a tracheal splints that I generate, this all needs to be made with a biocompatible material. So this is a big business area today. A lot of people are coming up with a biocompatible material. In fact, if you look at this printer, there is a company by the name Ostepore, and this Ostepore can build a material exactly similar to your bone, and it is biocompatible. So the structure that it is creating is a bony structure, and this bony structure will go into your body, and eventually it will get accustomed with your body because the material that you have used is a biocompatible material. In fact, somebody who has worn out this articular cartilage, okay, this cartilage needs to be built. You can see that you are actually, some ligaments have broken and now you want to replace it. So such a structure, people are building this ligament which got torn, people build it and then they replace it via 3D. And this cannot be made, ki laga do isko andar. You just cannot put it. You have to build it for that particular patient. In fact, somebody who has suffered burns, you can create actually a wound healing vascular graft. You give him this graft, it has a wound healing medicine which is fitted. Eventually, it will dissolve and it will become a part of your body, and then this is becoming very, very common today. So medical domain is one of the very important area today, that is where this 3D printing is finding unusual applications. A large number of medical professionals are exploring applications of 3D printing into their domains. Let's look at buildings. And one of this idea came at MIT, and then the technology was given the name 1D contouring. Those who are interested to see a video, there is a commercial printer which has been made. You can click on this link and then you will be able to see the video that how the printer is built. But you can see actually there is a very interesting sculpture that is to be built. And then eventually you can design this sculpture entirely using a software. And then people have actually built this entire structure using a 3D printing route, wherein they put layer one over the other, and this is available as a fully functional thing. So you don't need to do sculpting actually. You need to deal with natural materials, and natural materials have a good tendency to sinter and fuse with each other. So you can build a 3D printing via this route. So this is called as a statue of David. You can Google and find out more about it. In fact, there is another variant. For a lot of wooden structures in the building, this technique has evolved, which is called as a platforming. Say for an example, if I want to build a structure like this, what do I do is at a software level, I make a CAD model. Eventually, I cut it into blocks. So these are wooden blocks that I'm going to make. Okay, and these wooden blocks would be manufactured using a computer-controlled wood cutting machine. And then these all would be numbered and they would be supplied to a 3D printing machine, and your 3D printing would eventually join them. So please understand, the technology is not layering, but it is breaking off a component into certain blocks of a standard dimensions. In fact, this particular route is becoming very, very popular in 3D printing of furnitures today. So all these blocks are being cut via 3D print, via this kind of route, but the governing philosophy for this is just a 3D printing wherein you discretize a component not in form of layers, but in form of small blocks. And this is a kid's game, a small kid's game that we all have might have played at one or the other point of time, either ourselves or with our kids or with our grandkids. So you can also build a sculpture like this. You can see this is a wood horse sculpture. You can convert it in form of small pieces, and then all these small pieces are basically joined together to build a structure of a horse. And this is used in a lot of movies to create artificial structures today, very elegantly looking and handsomely looking structures. In fact, if you talk about a full building, this was in a big news today. You can see there is a big gantry that has an extruder. It is trying to deposit the thing, and then these are the commercial photos, and this is what you can see as a news item which was published about 2 to 3 years ago, wherein people are talking about affordable 3D printed homes, just $10,000, and you just complete it in few days or few hours of time. So 3D printing of the building is going to be a reality today. In fact, Government of India has also funded some of the projects at IITs and NITs and different places to make this as a part of a Smart India initiative and Smart City initiative in years to come. Another important aspect is footwear design. In fact, if you look at big threes today, Adidas, Nike and Reebok, they have 3D printed shoes available. It is a very limited edition version which is available only for sportsmen. But if you look at Futurecraft 4D made by Adidas, these are 3D printed shoes actually. These are not made via a conventional woven technology. Or if you look at a fly print series of Nike, these are 3D printed shoes. And in fact, for a woman, a lot of people have actually started thinking about fashion shoes. Can they be built via a 3D printing route or not? Clothes. So these are some of the keywords that you can try: pangolin 3D or wardrobe of future. This is what, in fact, such kind of components people are trying to look via building using a 3D printing process. In fact, this is a designer from Italy. You can see many items that he tried to print via 3D printing route. A very nice sofa where he is elegantly sleeping. It is designed the way in which he likes to sleep, or he likes to sleep. Okay. The other picture which you see is that lamp design, the way in which it will throw lights in the room in a dark. It is very elegantly designed, entirely 3D printed structure. The next one is a 3D printed statue. In fact, 3D printed monuments like this are also becoming a reality today. This is printed using a binder jetting or an SLS technology, or a 3D printed chair. So depending on your own ergonomic needs, I can build a seat for your own choice, and then it's basically having a lot of applications. In fact, this is market of future. Printing of food is becoming a reality. In fact, Sir Patel has mentioned about chocolates. In fact, there is a world's largest chocolate making company. You all know Hershey's, not largest, but one of the very famous Hershey chocolates. So this is a Hershey chocolate printed. In fact, another one which you are seeing is a PRISA printer, which is made by NASA to print the 3D printed foods for astronauts, because they have not done anything wrong. They should not be eating a frozen food, rather they should be eating a fresh food, and this 3D printer will print a fresh pizza for people to eat over a period of time. In fact, this food printing I will take in a little detail, because this is also mentioned as one of the important items by Government of India in the future trend, in a lot of engineering institutes which are, or science colleges which are looking at food technology as a branch of engineering or science. For them it is very, very important. So people, when they try to print about food, these are three different ways in which people have explored. You can create it via an inkjet process. We have talked about an inkjet process earlier. You can also create a food via extrusion process, and you can also create it via a heating mode. And in fact, there are different processes which are developed. So in fact, inkjet can be a continuous or a drop on demand. So in fact, there are machines which can supply a continuous liquid. Eventually, it solidifies your food, or you put a drop based on your demand. So when drop on drop technology and drop on powder technology, so it's a hybrid. You put some means powder and some means drop only. In extrusion, people have talked about a phase change extrusion and a non-phase change extrusion via gel. Can I use it via melting extrusion or by powder layer binding? So they just put powder, and then the powder is binding in form of, so powder candies, all of us must have eaten at one or the other point of time. So these powder candies can be made via this heating mode route. In fact, if you want to look at inkjet technologies, there is a company in US by the name Foodjet. The YouTube video link is given to you. You can watch videos. In fact, they have large variety of machines. And in fact, their machine uses 4 elements. One is a platform, which is a depositor. Then there is a depositor head from which the food particles are going to come. There is a supplier system, so this is a storage, so which will include pump and the food ingredients. And then there is obviously a computer controller and the software, which is called as a Foodjet Designer Studio, their software. So this you can see in form of a video in order to appreciate commercial food printers are reality today. In fact, this is a photograph of a Hershey's extrusion grade chocolate printer, and this is kept in the museum of Hershey. So when you go to a Hershey plant, you will see this as an item, and they also sell 3D printed chocolates today to the visitors who are coming to the Hershey plant to see that. You can see typical chocolate shapes that are being fabricated via 3D printing route, which are very different compared to and very unique compared to the other chocolates that you get in a market. In fact, you can get a chocolate to gift someone on his own name on a birthday as a gift. This is what is becoming very, very common today. In fact, there is another company in USA which uses heating based technology to make candies. The name of a company is Candy Fab. And if you look at the nice candies or donuts which are made by them, these are all wonderful. This entire tray has been printed in a single setup, or this is printed as a single unit. So these Candy Fab machines are also very, very popular across United States and developed countries. Okay, so these are some of the unusual applications where you can think about yourself. With this, I would like to conclude my talk here. I think we are almost running out of time, and in case if you have any questions, please feel free to ask. You can also drop me an email at the email address given. If you want to look at the activities that we do, you can see the website. What are the facilities that we have in terms of 3D printing and other technologies on the website. So with this, I would like to conclude my session, and I would leave it open for the organizers.
Thank you, sir. I would like to inform you that we have received 2 to 3 questions, and we have already published it. So, you want me to read it out, or
yeah? Just so let me go to. So I'm just going there. Live event Q&A.
Yes.
Yeah. So there are. So I think how SLM is different from SLS. Okay. So this I have anyway answered. Selective laser melting is a technology which melts the wire, while SLS is a technology that fuses the powder via laser. So if you look at an essential difference, the liquid droplet falls in SLA, while in an SLS, the powder is already available in form of a layer. That is where you heat, so the powder gets fused. Okay. Another question is, can I make multicolor object? If yes, then how? So say for an example, if you look at material jetting technology, let me answer this via two technologies. So I have talked about the material jetting technology. This material jetting technology works on a principle similar to your inkjet printer. So you must have seen a color inkjet printer. The obvious question that you should have is, how color inkjet prints different colors on a single paper, isn't it? So when I go to a color printer, he has the same printing head, but there are large number of nozzles, and each nozzle can supply any color that you want from a color drum that you have. Which color drum it has to collect the liquid is available from the computer program that you have. The way in which you can take a color print, similarly you can build a single component with multiple colors using a material jetting technology. If you want to build it via FDM, what you need is you need many nozzles. So instead of two nozzles, a building material and a support material, I can have multiple color building materials. All materials are same, but their colors are different. So I can deposit them selectively in different areas. So in material jetting technologies and FDM, these both are available, but it is much more easier to achieve a multicolor object using a material jetting technology. So if you talk about the machines, Stratasys has a machine that can give you at least 8 different colors and their combination. Not only multiple colors today, in fact, Stratasys has a machine which is called as a Connex series machine. A Connex series machine will give you multi-material also. So if you assume I have a component, say for an example, this is a different color component. I have one color and other, but this is made up of one material and this is made up of another material as a single piece. This is also possible today. So to the viewers, I would advise to see Connex series machines. I'm not advocating, but this is one of the very popular machine available in the market to print multi-materials. How many nozzles at a time is possible? So typically more than 100 is very, very common in material jetting. Very, very common. So I mean, this answers all the questions that are mentioned.
So as we have come towards the end of this session, I would like to thank Dr. Kaushal Desai for sharing your time and knowledge with us, sir. We are really grateful for the efforts that you have put in today. Lastly, I would like to thank our Honorable Principal Secretary, Ma'am Anju Sharma. I would like to thank Director Higher Education for constantly providing their support and guidance in conducting these sessions. Once again, I thank all the participants for their time, for being a part of this session, and a heartfelt thanks to Dr. Kaushal Desai also. Thank you so much.